So we're going to move on today to start looking at the equilibrium constant. So this is a calculation that kind of helps us to get some more information about the reaction and its equilibrium. So last lesson we looked at how some reactions are reversible and therefore can exist in equilibrium and others are irreversible. So from now on we're going to be focusing mostly on those reversible reactions that exist in equilibrium. So if it does exist in equilibrium, then it will have an equilibrium constant, which we denote with this little symbol Kc. And what Kc actually is the ratio of the concentrations of products to the concentrations of reactants present at equilibrium. And remember, we know that it's at equilibrium when the rate of the forward and reverse reactions are equal. And Kc gives us some information about how far a reaction proceeds. Does it form a lot of products, or does it just form a little bit and it's sitting mostly towards the reactants? Key thing here is it doesn't give us any information about the rate of the reaction. So in the part A that we looked at to do with rates of reaction, we looked at how fast something's going or how slow. Kc doesn't give us any information regarding this. So here I've got a general reaction where I've got my reactants and my products. What we've got here is this little symbol in the middle, which is the moles of each of those species. So it might have a 2 in front of it, or a 3, or nothing, which means 1, which we get from balancing the equation. So how we then put this into Kc is we have the products divided by the reactants. Now remember, it's concentration, so a really key part here is these square brackets here mean concentration. So if you do brackets that look like this, that doesn't mean concentration, and this would be marked wrong. So it does need to be square brackets like this. So because it's product concentration over reactants, I'm going to take my first product, which is C, and put this in here. Now I'm going to put to the power of whatever this number is before that species. Likewise D, and then I'm going to put A and B on the bottom as those are my reactants. Also really important, these are multiplied together, they're not added together, for example. So the concentration that we're measuring here is in moles per litre, which we'll have a look at later, but really important we use the square brackets and not those regular round brackets. Okay, so the Kc value that we end up calculating does not have units, because what we're doing is moles per litre divided by moles per litre, so they just cancel out. So when we give our answer for Kc, it doesn't have units, it's just a number. Solids and liquids are never included in the Kc expression, so if it's got a little s or an L, we're going to leave them out completely. And the reason for that is they're typically so pure that the concentration of them is so high and doesn't really change with equilibrium. So we just assume that they're unchanged and we'll leave them out altogether. So Kc that we get when you're given a Kc value is assuming that this reaction is at 1 atmosphere of pressure and at room temperature. Later we'll see if you change these conditions. If we change the temperature, for example, the Kc value will be different. So the value that we've got here is for room temperature of 25 degrees. So just like I said before, if it's got a liquid here, it's not included. This includes liquid water. Water is only included if it's gaseous. So for example here, I've got calcium carbonate, which is a solid, not going to be included because it's a solid. React in equilibrium to form calcium oxide, again a solid, so we're not going to include that, plus carbon dioxide gas. We will include that. Now remember, our Kc is products concentration over reactants. So my product that I'm going to put in, carbon dioxide, put in here. I don't need to put any number up here because there's nothing in the front here, and it's not divided by any reactants because our only reactant is a solid, which we're not going to include. So let's do some together so we can start to get quite good at this. So I am going to put up here just as a reminder, Kc is the product concentration divided by the reactants concentration. Always products over reactants. So here are my products here of this reaction. So what I'm going to have is Kc is equal to the concentration of N2. There's nothing in front of that, so I'm not going to square it or anything. Times the concentration of H2. But I've got 3 moles of this in my reaction, so I'm going to do to the power of 3 up here. Now those are both gases, which is why they are present in my Kc. If I have a look at my reactants, also a gas, so I do need to include that. Concentration of NH3, being really careful to get square brackets and not rounded brackets. And I've got 2 moles of that in my balanced equation, so I'm going to have to square that one there. So that's my Kc for this equation. So when a question says write the equilibrium expression, that's that. Okay, the next one here, also all gases, so they're all going to be included in this one here. Okay, so I've got Kc, again, products we're looking at first. Here's my products. Concentration of NH3, and there's 4 moles of that, so to the power of 4. Over, I've got N2, I've got 2 moles of that one, so squared, times H2, and I've got 6 moles of that one, so to the power of 6 for that one there. Okay, down the bottom here I've got an aqueous, which means this is dissolved in water. A liquid, I'm not going to include that because it's a liquid. Another aqueous and another aqueous, so those will both be included. So I'm going to have Kc equals the concentration of this one, nothing in front of it, so don't need to put anything else there, times concentration of H3O plus, nothing in front of that, so that's fine, divided by the concentration of that one there. Again, nothing in front of it, so I don't need to put any exponents in there. Okay, so once we've been able to write those equilibrium expressions, which are typically for achieved, we can then input some numbers and some concentrations that are given to us and actually calculate Kc. On the other hand, some questions just give you Kc and ask you to interpret it. So how do we interpret that number that we get given? So like I said, the value of Kc is an indication of the extent to which the equilibrium is leaning towards the product or leaning towards the reactants. Now remember, a really common confusion is that equilibrium means same amounts of product and reactants, which is definitely not the case. It's the same rate of the forward reaction with the same rate as the backwards reaction. So they're occurring at the same speed. Doesn't mean that we've got more reactants or more products. Sorry, doesn't mean we've got the same concentration of reactants and products. So once we're able to calculate this, if Kc is large, and by large I mean bigger than 1, like a lot bigger than 1, then this is telling us that at equilibrium there's far more products than there is reactants. So this reaction is product favoured. Because remember, Kc is product concentration over reactant concentration. So if I've got a big number on the top divided by a small number on the bottom, it's going to give me a big number. So I've got more products than I do reactants. However, if Kc is less than 1, then at equilibrium it's going to be well over to the reactant side. So I'm not forming much product, I'm left with still a lot of reactants. Because what I've got here is a small number divided by a big number is going to give me a number that's really small. For example, if I had up here 1,000 divided by 2, that's going to give me still a big number, 500. However, if I did 2 divided by 1,000, that's going to give me quite a small number. If I've got Kc is equal to 1, then that's telling me that at equilibrium I've got the exact same concentrations of products and reactants, which is not normally the case. So So it's either going to be a lot bigger than 1 or a lot less than 1. Okay, so here's a question that we can have a look at together. So for the reaction H2 gas plus chlorine gas in equilibrium forms hydrochloric acid gas. The value of Kc is 4.0 times 10 to the power of 31. So if I was going to write my Kc for this here, got my product, HCl, which I'm going to do to the power of 2 because of that there, divided by H2 times Cl2, which don't have any numbers to square them to. Okay, so my Kc value is 4.0 times 10 to the power of 31. So that means that I'm moving the decimal place 31 places down this way. So this is a huge number. So it's really large, and definitely greater than 1. This indicates to me that at equilibrium, so only at equilibrium, there's virtually no H2 or Cl2. This reaction is very product favoured. So I've got a really big number on the top here, really small concentration down the bottom there. This gives me a number bigger than 1. For example, if I have a look at ethanoic acid here, let's write that Kc. CH3COO minus times H3O plus. And remember, I'm not putting the liquid water in because it's a liquid. Its concentration doesn't really change. We assume it's a constant. This is my Kc for this one here. Now my Kc value, once you actually calculate this, is 1.8 times 10 to the minus 5. Now what that minus 5 means is I'm actually moving the decimal place over this way 5 times. So what I'm going to end up with is this, which is definitely less than 1. Okay, this is a small number. So what that's telling me is I've got a high concentration of this one here and a low concentration of this one here. Small number divided by a really big number is going to give me a really small number. So what I've got here is this tells me it's a really weak acid. I don't have much of this product. I've got a lot higher concentration of reactant. So this reaction tells me this is reactant favoured, or the reverse reaction is favoured. Sometimes you'll get a question that asks you to calculate Kc to figure out, is this reaction at equilibrium yet or is it not? And how we do that is they'll give you values for all these concentrations, and then we just need to compare it to the given Kc value. Now because it's not a constant or at equilibrium, we're not going to call it Kc anymore because that wouldn't make sense. So we just call it Q, the reaction quotient. So we're just replacing Kc with Q, but it is the exact same calculation. We're just going to substitute into our Kc expression. So if Q is a lot bigger than Kc, then what this tells me is at this point in particular, I've got a lot more products than I do reactants at equilibrium. So what this is telling me is the backwards reaction needs to be favoured to try and reach equilibrium and use up those products. If Q is less than Kc, that means that there's more reactants present at equilibrium. So I haven't yet made enough product to reach that equilibrium position. So the forwards reaction is favoured to try and reach equilibrium. If Q is the same number as Kc, then our reaction is already at equilibrium. So here's a past paper that we can do together. So the contact process is used industrially in the manufacture of sulfuric acid. One step in this process is the oxidation of sulfur dioxide, SO2, to sulfur trioxide, SO3. Write the equilibrium constant expression for this reaction. Right, so I'm going to start with my products here. Remember, products go on the top in square brackets. SO3, I'm going to square that because it's got a 2 in front of it. Divided by, let's look at my reactants, SO2 squared times O2, which doesn't have anything in front of it, so I'll just leave that as is. Okay, remember if it's got nothing in front of it, it means it's just 1. All of those are gases, so they will all be included in my Kc rather than leaving them out. Okay, now we're going to calculate the equilibrium constant for this reaction at 600 degrees using these concentrations here. We're going to substitute into what I've already got up there, SO3, 0.0930 squared, don't forget the squared, divided by SO2, 0.100 squared, times oxygen is 0.200. Now if I were you, I would be putting this in your calculator, do this bit first, and then do that top bit divided by shift answer. I don't have my calculator with me, so let's have a look here. You should get 4.32. And what does that tell you about Kc? Well, 4 is bigger than 1, which means that there is going to be more products than reactants at equilibrium. So you can see this goes up to a merit. Okay, here's another question here. Hydrogen can be produced industrially by reacting methane with water. An equation for this reaction can be represented by this here. The Kc is 4.7 at 1127 degrees Celsius. Complete the equilibrium constant expression. So, what we should have here is Kc is equal to H2 to the power of 3 because there's 3 moles of that in our equation. And I'm going to multiply that by the concentration of carbon monoxide, that's CO, divided by, now I need to look at my reactants, CH4 concentration, this is all square brackets, you'd be marked wrong, not achieved if it is not square brackets, times H2O. Now we're including water here because it's a gas, not a liquid. Okay, next question. The concentrations of the 4 gases in a reaction mixture at this temperature are found to be here in the table. Use these values to carry out a calculation to determine if the reaction is, in fact, at equilibrium. So we're just going to substitute all those numbers. You should get 3.6, which is not equal to 4.7. It is less. So therefore that means, no, we are not at equilibrium. To get to equilibrium, if we go back to this one here, so in this case our Q was smaller than Kc, means that we've still got some more reactants left over. So we've still got some more methane, that CH4, that hasn't turned into product yet. Once we've got some more product, then we would reach equilibrium. Might need a bit more time. Okay, a higher excellence kind of level question is rearranging this equation. So if you're not so great at algebra, you're going to need to practice this a lot before the exam. Nitrogen can also be reacted with oxygen to give nitrogen dioxide, NO2, and this is the Kc expression. They've given us the value at 25 degrees, which is 8.3 times 10 to the power of minus 10. So that is a very small number. So we've got 0.9083, so a really small number, definitely less than 1, which is telling me that I've got a lot of reactants and not much product at 25 degrees. So if this was my job to make nitrogen dioxide, I'm going to need to figure out a way to push it towards the products, because naturally this is lying heavily towards the reactants and I'm not actually making much product that I can sell. So in future lessons we're going to look at how can you push this towards the products. Alright, calculate the concentration of nitrogen dioxide if the concentration of oxygen is 0.230 moles per litre and nitrogen is 0.110 moles per litre. Okay, so we're going to need to substitute these values into our Kc expression. When it says give your answer the appropriate significant figures for chemistry, we need to have 3 significant figures for all of our answers. Write yourself a note, 3 significant figures. Alright, so you're going to need to rearrange it like this. So you're going to bring up the bottom part, the reactants, onto the other side of the equal sign by multiplying it with Kc. Then because our NO2 concentration is squared, we're going to need to square root that answer there. So what you should get is 2.2 times 10 to the power of minus 6. Now the units this is asking us for a concentration is moles per litre, and it needs to be in 3 significant figures for an excellence. So achieved, you can get one step, kind of like substituting the numbers in. Merit, you can calculate it, but maybe not the right significant figures or units. Excellence, you've got everything together in there. So you will need to practice these calculations, and there is loads on Education Perfect for you to practice.